Very good morning, students. In today's class, we are going to learn about what are the applications of an operational amplifier. So far, we have studied what is an op amp, what are the ideal characteristics of an op amp, and what are the parameters related to the op amp, and how op amp is acting as an inverting and non-inverting amplifier, so on. So now it is the learning of applications of the operational amplifier. So the first application is Op Amp Adder, or it can be named as a summer. So here the circuit what I have shown, it is an inverting adder circuit. Inverting in the sense I have to give the input at the inverting input terminal, whereas the other non-inverting input terminal will be grounded. Hence it is named as inverting op amp adder circuit or summer circuit. So an op amp adder, it is a circuit which performs addition of two or more input signals which are applied at the inverting input of the op amp. So here I am going to apply the input voltages across the inverting input terminal. So I can apply more than two input signals which I want to add it. So in other words, we can define the adder as a circuit which is used to perform addition operation of the signals which are applied at the inverting input terminal as shown below. So the circuit construction is such that the input voltages has to be fed to the inverting input terminal via the resistance, respective resistances R1, R2 and R3, and current across this R1 is taken as I1, across R2 it is I2, and across R3 it is I3. And the inverting input terminal is grounded, and there is a feedback resistance RF which is connected between the inverting input terminal and the output terminal V0, and the current which flows across the feedback resistance is taken as IF. So we can identify a node across the inverting input terminal by applying the KCL law, that is Kirchhoff's current law. We can assume that at the node, inverting node, the potential is 0. That is, since the inverting input is grounded, by using the concept of virtual ground, we can say that the inverting input terminal is also grounded. Hence, it is written as G is equal to 0 in the diagram. And with the help of the Kirchhoff's current law, so considering this as a node, so whatever the current which is flowing towards the node is equal to the current flowing outside the node. So we can write IF is equal to I1 plus I2 plus I3. And what is IF is 0 minus V0 divided by RF, and I1 can be written as V1 minus 0 by R1, and I2 as V2 minus 0 by R2, and I3 as V3 minus 0 divided by R3. So let us solve this equation and we'll find out what is V0. So finally we are getting the output voltage V0 is equal to minus RF of V1 plus R1 plus V2 by R2 plus V3 by R3. So let us assume that if R1 is equal to R2 is equal to R3 is equal to R, that is all the three resistances, I am going to make it as R. Then the simplified output voltage equation is V0 is equal to minus RF divided by R into V1 plus V2 plus V3. Again I am making RF is equal to R, so that I will be getting the expression for output voltage as, so if we make RF is equal to R, RF and R will get cancelled, and we will be getting V0 is equal to V1 minus V1 plus V2 plus V3. So hence it is observed that the output voltage is equal to sum of the inverter sum of the input voltages. So finally from this output equation I can conclude that the output is sum of the input voltages applied at the inverting input terminal. So the next application of an op amp is voltage follower. So voltage follower is a circuit in which the output voltage follows the input voltage. Then I can name it as a voltage follower. So the construction of the voltage follower circuit is such that for the non-inverting input terminal there is a input voltage Vin is given. So at node B we can write the voltage at node B as Vb, which is equal to Va. And for the inverting input terminal, it is connected directly to the output terminal V0. So this is how I am going to make the circuit to work as a voltage follower. And using the concept of virtual ground, both the input terminals are at the same potential. That is VB is equal to Vin, which is same as Va. So I can write Va is equal to Vb is equal to Vin. As the node A is directly connected to the output, I can write V0 is equal to Va. So in the voltage follower, we are able to find out the gain is 1, that is the gain is unity, and V0 is equal to Vin. A voltage follower can also be named as source follower. As it is equal to Vin, I can name it as a source follower, or it can be named as a unity gain amplifier. That is the gain of the voltage follower circuit is 1. And it is also called as buffer amplifier or isolation amplifier. So finally we can write the expression for the output voltage as V0 is equal to Vin. In the right hand side I have shown the waveforms of the input and output voltages. So first it is the input voltage waveform, and second one it represents the output waveform, which is same as the input voltage. So thereby I can conclude that this circuit acts as a voltage follower, that is the output voltage follows the input voltage. Next it is a integrator. So the op amp circuit, it is going to act as an integrator here. So in an integrator circuit, the output is the integration of the input voltage. So whatever the input voltage we are going to feed, the output seems to be integrated of the input signal. So the circuit diagram is constructed such that any input voltage Vin, it is applied at the inverting input terminal of the op amp through the resistance R1, and the inverting input non-inverting input terminal is grounded, and there is a capacitor connected in between the inverting input terminal and the output terminal V0, and it is named as CF. So this is the construction of the integrator circuit. So let us see whether the output voltage is the integrated of the input voltage or not. And as we know, the potential at Va, it is equal to Vb, and which is taken as 0. Why? Because the potential at B is directly connected to the ground. Vb will be 0, which is same as Va. Hence Va is equal to Vb is equal to 0. And let us assume the current I1, which is flowing across the R1 resistance, and I1 can be written as Vin minus Va divided by R1. Since Va is equal to 0, I1 is equal to Vin by R1. And we can write the expression for IF. IF is termed as the current which is flowing across the feedback path, that is across the capacitor. So IF is equal to CF into the difference in the voltage levels divided by dt. So dVa minus V0 divided by dt, which is equal to minus CF of dV0 divided by dt. And the other assumption what we have made is the input current is 0. So I1 passes across RF, which is same as IF. That is I1 is equal to IF based on the assumption. So let us equate I1 is equal to IF, and we'll try to find out what is V0. So for that, integrate both the differentiate both the equations. We'll be getting dV0 divided by dt is equal to minus Vn divided by R1 into CF. Now let us integrate to get V0 separately. So integrating with respect to t, integration of dV0 divided by dt into dt is equal to minus 1 divided by R1 CF integration of dv na integration of vn divided vn into dt. So integral and differentiation will get cancelled. So we'll be getting the final expression for the output voltage as V naught is equal to minus 1 divided by RF R1 into CF integral of Vn into dt. So this final equation shows that the input voltage is integrated and it is appeared at the output point. And the term 1 divided by R1 into CF, will call it as gain of the amplifier, and the output is also inverted. So it is it acts as an integrator here.